Hello and very good evening once more. Welcome to today's session. This is the concluding session on what we were discussing on Einstein's general theory of relativity. And today what I would like to do is that I would like to conclude this setting the background that we have done. And now we would be talking about what is called the light cone, which is definitely has been taken forward in terms of the special relativity, etc. So, first of all, a very good evening, and I would like to know that whether my audio part is clear or not. I think it is. So, I really don't want to give you a recap because most of you who have been Aeon drawing. Hi, sir. Hi, Aeon. Is my audio clear? Can you just put up a yes or no? That would be great. So I just want to make sure that yesterday, those who have attended the session, you have attended, and those who have not attended, it is there in the live section, which you can go ahead and watch it. However, I would like to start today's session with a quick recap, as you can see here, understanding space-time geometry, etc. And today what we would be doing, I've already talked a lot about the gravity part. Shomojit, good evening, warm welcome. I think I know you. You have been an old subscriber of my channel. Okay, and we talked about this truth of gravity. We also talked about flat space-time, isn't it? We talked about Minkowski space-time. Also, most importantly, we talked about what is called a contravariant vector. So what we understand from yesterday's discussion is that we have set the stage for what is called the flat space-time. These values are actually zero. That means they are perfectly okay in terms, let me go to that slide. These part are zero. That means they are perfectly okay. They are not mixing up space and time. And these values actually tells that space is different and science is different. Okay, you're preparing for physics Olympiad. Okay, great. Congratulations and all the best. So from here, what we will do today is that we will straight away go to, just a second, let me go to the slide. Right. So what we will do is that in every kind of understanding that we get in terms of special theory of relativity, or I would say general relativity, we always see that there is something which is called a space-time interval. Okay, just a second. I'll just adjust my camera. Yeah. It is a space-time interval. Okay. And this space-time interval, sir, I'm preparing for the, can it be beneficial for me to learn Lagrangian mechanics? See, Shomaji, Lagrangian is the basic fundamental of physics. So whether it is physics Olympiad or anything, I feel that this would be required for any part of a preparation. I don't know the history or the details of physics Olympiad, what would be the question, but Lagrangian is the key. You can, I mean to say, you should go ahead and learn Lagrangian. That there is no problem. There's no ifs and buts. Definitely it is one, and Lagrangian mechanics will be very helpful in understanding the other part of physics from classical when you move into quantum mechanics, etc. So definitely Lagrangian mechanics is one of the best. You can find out a video of mine. Let me give you the link to that video. It has become very popular thanks to all of you, and this actually explains the Lagrangian as a whole, right? This is a good video. Just hold on for a second. I will just take the how to learn Lagrangian mechanics by myself. It is difficult to learn Lagrangian mechanics. However, I can tell you a book which is written by, hold on, this is actually the problem is that whenever I start speaking on any live or I want to actually teach, there are so many questions come up, but it is okay. I will tell you the name of the book, Lagrangian Hamiltonian. Yeah, there is a book which is called this one, A Student's Guide to Lagrangian Mechanics, Patrick Hamel. Just let me share my screen. I will show you the book. Just hold on. How will I? Yeah. So present, share screen, window. Yeah, this one. Shomajit, can you see my screen now? Lagrangian mechanics. Just put me a yes or no. Lagrangian and Hamiltonians by Patrick Hamill. Can you see my screen? Yes or no? This is a very good book. And I can tell you the content is equally very good. You can see the content part. This is for self-learning. So kinematics, generalized coordinates, generalized velocity actually starts with that constraints, virtual displacement, conservation, everything is being covered. This is definitely a very good book for Lagrangian mechanics. Okay, let me stop the screen sharing and get back to the topic. So the basic thing is that here you can see for space-time interval, we always see a negative sign. Okay, and what we see is, okay, thank you very much. Welcome. And what we see is that there is a negative minus sign and there is a C. So what is this all about? Why we need a negative sign? Why we need a C, etc. So first, as you can see over here, that we had already covered this, right? ds square equal to this one. We know that if we take natural unit C equals to 1, then it becomes minus. So does this mean that time is negative? Most of the students, some of they ask this question, sir, minus dt means time is negative. No, dt is a small displacement in time, dx and dy and dz are small displacement in displacement. Now, as you can see that in space you can move left, right, up and down, but in time you can only move forward. Right? You cannot get back to time and become younger and see your youth again, right? So as you can see on the right hand side corner, we are all getting older. So that means time can only move in one direction, and that is what is called the asymmetric nature of time. Time cannot get back. So what we did in mathematics, or Einstein, what we did is the minus sign. It is basically telling that how we treat time differently from space. Okay, I hope you get my point. Time is totally different from space. Why time is different? Because in this coordinate system, we can move up, down, plus, minus, etc. But in case of a time, it can only move forward. How will we denote that it is a different thing? We put up a minus sign. So the common misunderstanding is that time has a minus sign. No, time does not have a minus sign. Okay, so if you see, for example, on the right hand side, please concentrate on the right hand side, you will see we have taken a minus plus 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 convention. Okay, now if, for example, if we take s square equals to, say, for example, I take the speed of light, etc., then what we can do is that we take s square equals to 0. It comes to that. Now if I increase t, keeping x the same, that means I'm increasing the time to 4 seconds, you will get this kind of a value, 7 times 10 to the power 6. So what it tells that more time separates the two events, the more negative the interval becomes. So if you go to the next part, things will become clear. So some of the books, they prefer a plus minus 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 sign. I was telling this earlier also. Here we have taken minus plus 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 sign. So it depends upon the convention. So this is called mostly minus, that is called a mostly plus. Now, what it is telling is that negative in this context is a sign, is a formula, and remember that negative does not mean it is a judgment, that it is wrong, etc. Okay, it is actually telling that time behaves differently than space in geometry, right? So we give time a different kind of a signature in the interval, not because time is negative, but because it behaves differently. So we want to actually denote symmetry in space versus asymmetry in time. Symmetry in space, that we can move up, down, left, right, but in time we can only and only move forward. As you can see that in case of delta x could be positive or negative, and if we square that, x squared will always be positive and it is subtracted from the interval. So similarly, time increases only, but its square is always positive. Either it is added or subtracted. So this is another reason we are doing this square. Okay. So if you see that ds curve, why we do the square terms like ct and x? Because to make them scale invariant. That means we will always get a positive sign. So on the right hand side, if you concentrate, are we squaring to make it positive? The answer is that it is totally different from Euclidean geometry. In Euclidean geometry, it is always greater than equal to 0. But in Minkowski space, it can be positive, negative, or 0. So this is basically the difference between space-time interval, the Minkowski space and interval space. Now, the question is that although we have said that time is behaving differently, and that is why we have put up a negative sign, but I think that you are not much convinced with this kind of an approach. Obviously, we are denoting time as minus because space is different and time is different. We understand that time cannot move backward, space can move backward, all this thing. But there is one important thing, that there is a mathematical part involved in that. And this mathematical part is called hyperbola in special relativity. Okay, I'm not going to teach hyperbolic geometry, that was demanding a different kind of a course. But what I would like to tell you is this. First, let us concentrate on the right hand side. Okay, we have a infinitesimal small distance dx and dy, and in order to understand how far it is, or if you want to calculate the length, simply the length of the black vector, then what we will do is that we use the Pythagoras' theorem. ds squared equal to dx squared plus dy squared. But on the other hand, when we come to the Minkowski space, dx is okay, but the y-axis is measured as time. And here there is something which is called cdt. Okay, we put the speed of light. I will come to that. Now here what happens, we will get a minus sign. And in order to, yes, good evening Vikramjit. So I won't call you Rockstar, I will call Vikramjit Singh. Okay, so what we are seeing from here is that the geometric construction of Minkowski space is that, as you can see, the Pythagoras' theorem is not working here, because we have got a negative sign. So in order to deal with this, we actually need a different kind of a geometry, and for that we use something which is called a poincaredisk model. Now don't worry about this term. This was Henri Poincaré who first, it is written as Henry, right? In French it is pronounced as Henri. So Henri Poincaré actually proposed a kind of a hyperbolic geometry, where the most important thing is that if you draw a triangle, right? In general, in Euclidean space, the angles, the sum of the angles of the triangle is equal to 180 degree. But here it is always less than 180 degree. Okay. And if you make the triangle smaller and smaller, closer the angle will come to 180 degree, but it will never reach 180 degrees, right? It looks something like this, which I have written. It will go like this. But you can think of the internal structure of the Poincare disk to be a kind of a circle, but it has radius 1. Okay, that is why it is called a unit circle. But as you go and go, try to get to the near, you will get farther and farther away. Okay, let me show you the animation of Poincare disk GIF so that you can really understand this. Okay. Let me share my screen, then you can understand what I am telling. Oh, okay. Present, shared screen, window. I cannot share this screen. Where is this? Just hold on. Okay. Okay, on the right hand side, oh, the animation is not being supported. I'm so sorry. The animation is not being supported. Anyway, this is actually how the Poincare disk looks like. Just hold on. Let me find out if I can remove. Stop sharing. Present. Share screen. Entire screen. Okay. Anyway, so this is how actually the Poincare disk actually looks like. That if you go to try to go to the nearer and nearer, you will never reach that. Okay. So let me show you another picture. It will be important. I'm coming to your question, Vikramjit. So here you can see. Okay. It is something like, I would say, if you wrap up a pizza, right? So this set will include all the cheese and sauce within the crust, but not the crust itself. So it is a kind of a Zeno's paradox, right? I would say Achilles is moving, the tortoise is further moving. Achilles is moving, the tortoise is further moving. So what is happening is that if you go near to the edge, you will never reach it. It will go further and further away. So here you can see in the general, I would say Euclidean space, you are measured as distance as 1 meter or so. But in a hyperbolic geometry, if you try to move further and further, you will reach infinity. So it will never take you. Forget about this suppose z equals to 1. This is a mathematical derivation which is showing that how the infinity is reached and you never reach to the edge of the circle. You will continue and continue and continue. Anyway, this is a Poincare disk. Now the question is that you might ask me that why we are dealing with Poincare disk. The reason is that Poincare disk actually gives a very easy understanding of a hyperbolic geometry. I will come to that part later. So here you can see that we are now trying to integrate hyperbolic geometry, hyperbola, Minkowski space and Poincare disk model. So here you can see if I draw an ordinary hyperbola, I am already getting a -1 sign. X squared minus y squared equal to -1. This is basically the equation of the hyperbola. And on the right hand side, this is the Poincare disk. But remember, why I am saying that if you stretch, it will go on further and further. So the left hand side, you can see the left hand side of the hyperbola, it continues and continues till infinity. Here also, and same thing when I am posting this hyperbola on a Poincare disk, same thing happens. The edge continues and continues, it never reaches. But remember, hyperbola and the Poincare disk are two different things. They are not the same thing. Why? Here you see that basically a hyperbola comes out of conic section, two-dimensional curve. A hyperboloid is a three-dimensional shape. And to a two-dimensional model, this is a projection of the hyperboloid, the three-dimensional model, on a surface which makes up the Poincare disk. So obviously they differ in dimension because this is two-dimension, this is three-dimension. They serve different roles and they are different in structure. So I just wanted to make sure that you understand that hyperbola is what we draw on the pen and paper on a graph. This is a graph where the left hand side and this part is going infinity. Hyperboloid is basically the three-dimensional shape and a projection of the hyperbola. I will show you the projection. That is why the Poincare disk comes in. Now here you can see that if I am taking the upper part, only the upper part of the hyperbola, then it will obviously satisfy this equation minus x squared minus y squared plus z squared equal to 1. Right? So hyperbolic geometry is what governs the shape. So hyperbolic geometry is the idea which actually tells you about the negative one. Now here you can see on the what we have done is that we have taken a hyperbolic shape, and if I shine a light on it on the top, on the right hand side, you can see that there is a torch which is shining. It will basically create what is called a Poincare disk. So this is called the projection. So the upper surface green is a two-sheeted hyperboloid. The Poincare disk is the gray part, and the red curve is the geodesic. That means these are just representing the straight lines, and the light which is shining from the top is basically the projection, and it actually creates the Poincare disk. Now you might ask me a question that how they are related to each other. So the answer to this is this. When we talk of hyperboloid model, hyperboloid means three dimension, so it emphasizes the shape. And when we talk of Lorentz model, which may mean to say the symmetry, the Lorentz group. Okay, so the Lorentzian metric, you can see it has got a negative sign. Hyperbolic curve, hyperbolas also have a negative sign. Okay, and here you can see the Minkowski spacetime also has a metric that looks like this. So all these things, the Lorentzian metric, the hyperbola, the hyperbolic metric, all of these things has got a negative sign. So actually, what book I read for this topic? Okay, I actually made it from my notes. Wait, Shubinoy Chokro. Okay, wait. I will give you a very good research. I will give you a very good book name. It says, just hold on for a second. I will just log into my WhatsApp It's a very good question, Rick Vishwas. I will just tell you the book name. So in general, you can find it in a book, any special relativity book that you can bring up, that you can actually understand. Any kind of a book. But here, okay, Rick, what you do, I have got this PDF. This is by Professor Shubinoy Chakraborty, page number 194. It contains this hyperbolic curve. It is on my WhatsApp. So after this session is over, Rick, just WhatsApp me with a hi. Tell that, sir, this is Rick from Physics for Students channel. I will send you the PDF, right? Page number 194. I remembered. I will send it to you. Right now, I don't have it. So, but Rick, I can tell you, you can pick up any book of special theory of relativity, hyperbolic curve. You can understand. Or what you can do, you can watch my video also. I have made it video number, the last video on my lecture on general relativity, right? You can find it. Or otherwise, send me a hi on the WhatsApp, right? I will tell you what to do. Okay. So here actually what it comes. So here you can see that the hyperboloid equation is minus. We use the same metric signature as Minkowski metric. But why? Because this is the geometry. The distance between 2 points is not measured by what is called a Pythagoras' theorem. It is basically what is called a hyperboloid. And here you can see I have traced, this is not necessary. It started with the early Greeks, then the hyperbolic geometry for Lobachevsky, Janusz Bolyai and Gauss, then etc. So basically what I am trying to tell is that in this idea of negative sign, this is being borrowed from mathematics. So the physicists imported that idea from mathematics, which actually was there. Okay, which was actually there from the concept of hyperbola, and it actually came up. I would like to skip this part, but okay, let me tell you that in case of a hyperbolic Pythagorean theorem, how do we do? So just have a quick look. Don't need to go. I think you all know that cos hyperbola equals to cos hyperbola A and cos hyperbola B. Now, what is important in this slide which you are watching, you see this when I am comparing the so left hand side bottom is basically the hypotenuse in a hyperbolic curve. It is approximately equals to 1.49, but compared to Euclidean geometry it is 1.41. I have taken the unit value 1 square simple. But what I'm trying to tell is that you see in hyperbolic geometry the hypotenuse is larger than in Euclidean geometry because it requires some more space. Hypotenuse means on the figure the C part. Okay, so hypotenuse is 1.49, but here it is 1.41. That means it spreads out, and that is the beauty of hyperbolic geometry. The sum of the angles will always be less than 180 degrees. Okay, here you can see. Okay, now let me explain this part. This is very important. Now you can see that if I draw a vector, this is actually coming out of the animation. If I draw a vector from O to point P, can you see this slide? Right hand side, if I draw a vector from point O to point P, then if I ask you, Rick, maybe I can ask Rick, right, a question that how many vectors or line segments can I draw from O to P? How many lines? We can draw many lines, 1, 2, 3, and so on, right? So I can reframe the question telling that what is the locus of all the points that are equidistant from the origin? What is the locus? So you might say that I can draw infinite, many lines, right? But in Minkowski space, what is the locus of all the points that are equidistant from the origin? What is the locus? Now here actually the problem comes. So before going in that, what you can see here, that this is a circle. And you know the beauty of it is that if the circle is symmetric. So from this point to this point, even if I rotate the circle in clockwise or anti-clockwise direction, the vector or the line length would be always the same. That means it is maintaining the symmetry. So that means in future, when we will be doing equation, we will try to get something which actually obeys the Lorentz transformation. Okay, so what is the line? So it gives you a circle. But in case of a Minkowski spacetime, it gives you a hyperbola. Okay, let me show you the next part. Yes, hyperbola, right. Now here you can see in the next slide. So if I draw this, this will be a hyperbola. So Now, it apparently seems that O to P, O to Q, O to R, O to S, these are different kind of a distance. Although I am saying that the distances are the same, but apparently it looks OP is bigger than OS. Now, why it is? Because you are seeing that in only spatial dimension, but this is space-time. So that is why it is. So we are plotting this on a chalk and board system, but our eyes cannot see the space-time part. So the hyperbola is a set of all events in the same proper time, and all these line segments are of equal length in space-time. So I have read something called Girard theorem, which no, Girard theorem is differential geometry. No, this is Subhashri Bhattacharya. Okay, yes, very good evening, Shubhashri. So Girard's theorem is something different. Yes, you are very right. Girard theorem actually speaks of this. You are very right. I think I've spoke about Girard theorem in case of a differential geometry. But Girard theorem, what is your name? Sai Shubham. So Girard theorem is actually something which is related to spherical triangle on a sphere. You are very right. I mean to say, if you talk, what is this Girard theorem? I would say you are absolutely right. These spherical triangles. But this is on a sphere. Okay. But what we are talking is of a hyperbola. So you just need to make your mathematics a little bit better. Don't take me wrong. What you have seen is basically, it is absolutely right. But Girard theorem, what it tells that in a spherical geometry, the area of a spherical triangle on a unit sphere is proportional to the, to the sum of the angle minus pi in radians. So it is A plus B plus C minus pi multiplied by the R square. Right? Now, I will tell you, this is a good thing that Shubham has brought up. Now, in Girard theorem, you see what actually is happening is that in Euclidean geometry, you know the sum of the angles of a triangle is exactly equal to 180 degrees, right? But on a sphere, the sum of the angles is always greater than pi, 180. Now, here you might ask a question, Shubham, that why it is so? You see the shape of the sphere itself has got a positive curvature. It doesn't spread out. I mean to say, hyperbola is spreading out like this. So the angles are folding somewhere. Are you getting my point? It is folding somewhere. So that is making the area less. It's a very good point. I would like to thank Shai Shubham for bringing this. So, Girard theorem is actually on a spherical surface. The sum of the angles are always greater than pi, and this excess over pi is directly related to how the curved surface of space is, and it helps to calculate. So I can tell you, you can imagine drawing a triangle on a globe. Okay, on a flat surface, it equals 180 degrees, but on a sphere, because the curvature, the triangle bulges out. Bulges out, it is something like, how will I say? Okay, let me show this on my mouse pad. So it will be something like this. I mean to say, it will bulge like this. You can see this bulging. This one, it will be something like this. And in hyperbolic geometry, it will be something like this. Are you getting my point? Are you getting my point? This is hyperbolic geometry. But the angles from here are curving out. But in a spherical geometry, it will bulge like this. And this bulging is actually causing the sum of the angles of a triangle more than 180 degrees. And Girard theorem, actually, I will tell you, is very useful for astronomy, differential geometry, geodesic, because we are dealing with globe. Okay, Shai Shubham, are you feeling happy? It's good. I mean to say, it is always great to question, because you are thinking in the right line. This is hyperbolic geometry, etc. Okay, so now you can see what I'm trying to tell, that the switch from circle to hyperbola, remember, it is not due to curvature. It is due to the change in the metric. Because the way we define distance in a circle is different. Robert Hunt, I learned more about the history of GR from this man than any other from other source. Great lecturer. Oh, thank you very much. Robert, from which country you are? Thanks, I'm elated. Okay, thank you. Yeah, today's session is much better. I don't know. I mean to say, initial two sessions there were very less people. I think they were not aware that I would be coming. So first of all, thank you very much, Robert. Robert is saying that he has learned the history of GR from me. So Robert, if you can tell me from which country you are, I am more than happy. I'm very much thankful for this wonderful comment. Thank you very much. At least I feel happy that apart from Florida, USA, I've been in India too few times. Okay, wonderful, wonderful. Thank you. So, Robert, I would say please stay tuned. I have got, I don't know how it will, but I have started with a wonderful, I should not say that I'm wonderful. Anyway, I'm sorry for that. But I would say that I am starting with a very layman's understanding of special theory of relativity. I'm designing the first video. Again, to tell you, Robert, this would be a complete course on special theory of relativity. But I am starting not with the mathematics, but something very different. Something about human perception. I think you will love it. I'm trying to launch it by next week. So, Robert, thank you very much. And you are from Florida, USA. I'm thankful that my lectures have reached you and you have learned about the history of GR. I will be posting more about the history of GR. Anyway, okay, Shubham, so you have got your doubts clear, right? So what I was telling you is that this is, remember that it is a change in the metric. It is not that why we are jumping is because we cannot find those values. So that is why we have to change it. So from here, I hope that you are all clear. Exactly. Sir is an exceptional person. Thank you. Thank you very much, Shubham. Thank you very, very much. Okay, so the point is that now you can understand, let me get back, that why this negative sign is coming. So the negative sign is nothing, it is coming from hyperbolic geometry, hyperbola, where all these negative signs are there. In a Lagrangian metric, it is actually there. In the Minkowski metric, it is there. And in a hyperbola also it is there. Now we come to the last and final. So you can calculate that hyperbola and you can see now that the hypotenuse is more in size, in measurement than it. Okay. Now, finally, I am coming to a very interesting part, which is this one. Why we put a C in front of a T? Now, you might have a question that T is measured in what? Seconds, nanoseconds, etc. And speed of light is what? Meter square, meter per second square, etc. So what is the problem? That in time is measured in something, speed of light is measured, and here is the catch. Okay. Pay an attention, you will learn something very good today. Okay, first of all, you see that space-time interval is written that s square equal to the, or I omit c square and write it as this. Okay, now why? Now remember one thing, that because we want all the terms to have the same physical units, especially unit of length squared. So spatial distances are what? In meters. Time is measured is in what? Seconds. So now if I subtract t square from x square, right, what it would be? It means, I'm coming to your question, Vikramjit. Second square plus minus meter square, what does it mean? Nothing. Meaningless. Nonsense. Okay, it is like subtracting the apples from the oranges, which means nothing. So by force, remember, by force we are converting time into space. Are you getting my point? By force, in order to make the measurement in a same pattern, we are converting time into space by multiplying by c, the speed of light. Let me show you the next part. Here you will see one by one you can leave. So c equal to meter by second, or we can write c equal to m by s. Okay, m by s means what? So if you multiply time by c, we get ct equal to m by s multiplied by s. S and s cancels off, so we get a m. So m by s means what? If 1 second passes, light travels c meters. Okay, now when I'm cancelling those, all this is, now ct has the same unit as x, y and z. So ct means, instead of plotting time as seconds or whatever nanoseconds, we plot it as ct. That means, which is how far light travels. Remember, how far, that means it is the distance. Okay, so when we are writing ct, remember that we are spatializing time. Now this is, you might say this is a problem. No, this is not a problem. This is a kind of a convention that we do in special relativity. so that we are, you see this slide, spatializing time. That means expressing time as how far light would go in that time. So Ct equals to 3 times 10 to the power 8 meters. That means it allows us to treat time and space on the same footing in a diagram or formula. Are you getting my point? We are by force making time as space. So we are cancelling the s out and we are measuring as meter. So when we take c square plus t square, we are just taking as x squared, y squared, z squared. We are measuring in terms of meter, right? So from there, finally, we get to this slide. Whenever we are writing Ct in the y-axis, remember that we are literally turning time into a space. And here we treat time as a distance traveled by light, use the same unit. So time t is like a spatial difference. So time is not time, it is space. Okay. Even though Ct units of length, time is still flowing forward and the minus sign in the metric keeps it distinct from the spatial axis. So that's all for today's podcast, live session. I hope that you have. Now, which book should I read to cover special theory of relativity? Prasun Kumar Nayak. Prasun Kumar Nayak's book on special relativity is very good. I am also preparing a series of lecture on special relativity. You can listen to that. I've not yet prepared. I'm making that. Special relativity. Hold on. Let me see my special relativity. Actually, there are many books of special relativity. Problem is that you need to understand, Bikramjit, what is your mathematical expertise, and based on that, you need to select the book. This is a good book which you can select. Let me share my screen. You can take a note or you can later call me up also. I can tell you. How was today's session? All of you enjoyed it? Do you think I should come in this kind of a session more often? What do you think? This is a very good book which you can read. A Primer of Special Relativity by P. Sardesai. This is a very good book. Thank you, Professor Shaunak. Oh, from Ottawa, after a long time. Long time. Okay, this is a good book that you can read. This is, it contains a lot of details. This is primer. That means it is making you prepared. Can you see the content? Einstein information, ether, then it will condense Lorentz transformation. It's a good book. It's a good book. Okay. Relativity, simultaneity, mass, momentum, energy. It is a good book. So this is for the initial level. You can start with this book. Okay. There is another book, Spacetime Physics. This is by Wheeler, John Archibald Wheeler and F.W. Taylor. This is a very common and a very popular book. But the problem I don't like about this book is that it is not properly mathematically written. It contains certain things. I moved you back to the top of channels. Okay. Thank you very much. Thank you very much. That is a compliment. Sir, any tips? Thank you, His Highness. Any tips for reading quantum mechanics for 12th graders? Yes. Don't take me wrong. I would say for initial quantum mechanics, Shubham, you should go to my all 21 videos on quantum mechanics, the mathematics. See, the problem I will tell Shubham, most of the students, before reading the physics, you should understand that what kind of mathematics you need to know to learn that physics. Okay, why I am telling? Because you start reading the book, you understand, and suddenly you get stuck up in a kind of a mathematics. For example, Bra-and-Ket notation, a probability distribution. Then you will say, oh, what will I do? Fine, I go to another book, I read probability, then again come back. So the consistency is lot. Are you getting me, Shumam? So I would say not a lot of mathematics, but initial level mathematics you can learn. I don't remember any book, but linear algebra, vector analysis. These would be the two first mathematics that you need to read. Okay. So you can go to my video 1 to 21, not 1 to 21, at least if you watch the first 10 videos, you will get an understanding of the math. Okay, complex number, not complex analysis, but complex number you need to know. Once you get a good kind of an understanding of this, then you can go and start with quantum physics. Quantum physics, if you want, let me show you. Wait, quantum mechanics, if you want to show that if you start with the basic easy reading of quantum mechanics, then what you do, Shubham, is that you go to the Feynman lectures on quantum physics. Just type out Feynman lectures on quantum physics on the internet. It will take you to the website and you can learn from it. That is the best thing. The best lecture from the best person in the world, Richard Feynman's lecture on quantum physics. There is no alternative to this book. I will simply tell you upfront, there has been no book or no content, no lecture better than Richard Feynman's. One is electrodynamics, another is quantum physics. And he won the Nobel Prize only on quantum physics, actually, right? So that is one. So go to Feynman lectures on quantum physics. That would be something very good. And go and learn the basic mathematics. Don't fear that it will take a long time. It is not good. So see, I will tell you, today in college, I was talking to this research advisors. You know, we have research wing. So there are a lot of research advisors who are coming from the, what I would say, humanitarian background. They don't have a mathematical background. So problem is that there are other people who are, other than science, they are submitting their research papers. And then they have got data, so they have to do a hypothesis, p-value calculation, standard deviation, mean, median, mode, etc. So obviously they're getting stuck. So they told them that, sir, why don't you educate us on the basic of mathematics? So I will be starting a course on my college to teach the basic probability, not in details, but in general, what is probability distribution, mean, median, mode, then normal distribution curve, what is the bell curve, 2 sigma, 3 sigma, p-value calculation, z-value. And from there, if there is a research, how do you know what is the sample size that they would take? How do you know that how you can refute a hypothesis? What is a null hypothesis, etc. So I know a complete writing of a research report. It's quite elaborated, and I actually deal with that. So I would be teaching them the basics of probability theory. I mean to say statistics. So same goes for you and others, that don't fear mathematics, learn the basics. Otherwise, all the understanding will be problematic. You will feel that you have understood, but you have never understood. Let us be clear. Stand in front of the mirror. I have got a mirror here. So stand in front of the mirror and tell, do I really understand? If not, no problem. Don't feel shy. Go to my videos, consult with me, talk to your professor, talk to these books, read these books and learn the mathematics first. Learning mathematics first will give you a better understanding of physics. Otherwise, it will be just, a kind of a physics where nothing actually stands out. So that's it. So thank you very much. I think I have answered to all your questions, and tomorrow I am not coming. Thank you, sir, for your session. So sharing your session in WhatsApp. Okay, thank you very much. You have friends in WhatsApp, right? So tomorrow I am going out a little bit with my family. Sunday we have got a podcast. Remember, Sunday 8 p.m. on this channel. Dr. Arturo Di Giorgi, standard model particle physics. A lot of interesting things. I have already got a short video coming up tomorrow at 9 o'clock where these things will be given. And Monday onwards, again, my classes and mathematics, etc. So it's good to talk to you. So I will be keeping you posted on so 2 podcasts coming up tomorrow, day after tomorrow on particle physics, and on 22nd of June with Dr. Diksha on quantum gravity, string theory, things like that. So, and I will be continuing with my lectures on making videos on special relativity. You will love special relativity, I can tell you. General relativity will go on, differential geometry will go on, and I'm planning to start the first video and fresh series on quantum field theory. Not much of mathematics will be required. I will do a step-by-step understanding of quantum field theory. Things will be good. So great thanks to Shai Shubham. You have loved it. So great. Vikramjit Singh, thank you again for coming. Only my request is that share, please do share, because see, I will tell you, My YouTube channel has not got a 1 million subscriber, right? But I can tell you this much, that I believe, I'm not boasting, that whatever the job I'm doing is good for the education purpose. That is why YouTube has sent me a mail that now my videos will be getting embedded to foreign universities. It is called what? YouTube Education Player. And they would be playing my videos over there. So I've got that status that YouTube has recognized my channel as a purely educational channel, no entertainment, nothing. So please do share. As much as you share, other people who don't know, they might be struggling like you, they don't know the books, they will be benefited. So my basic purpose of my life around these 42, 43 years, I have to say, sorry, I told about my age, is basically to educate more and more. So more people educate, there will be less corruption, the society will be better, less will be the fight, and people will make something good out of it. So share my videos, tell your friends that here is a channel where you can talk. I generally respond to all my WhatsApp queries, except on my lecture I cannot do. Now the college has put up in me in various departments, soft skill training, statistical training, research analysis, paper reviewing. So I sometimes get very tired. I mean, in fact, today I was also lying. I was thinking to cancel that, but I told that, okay, I've told my children to come. So it is. I mean to say, it's a very hectic life. Eyes and mind get trained up. Anyway, so take care. Goodbye. Yeah, I will announce again when I'm coming online. But these podcasts, etc., will be there. Thank you. Thank you very much.